Hi everyone. So the idea of this talk is to not have a super critical mathematical lecture around deep learning, since you guys have already seen a lot of flavor of deep learning. So the formal title of the talk is From Statistical Models to Modern AI Systems. But largely what I want to discuss is how deep learning has given rise to trillions of dollars of wealth for a lot of people, especially in the Silicon Valley. So we'll talk about a lot of unknown men who have given rise to the modern AI industry and how in the whole race we people as engineers got to make a lot of money out of it, and how people are still making a lot of money, and how deep learning has given rise to this whole $1 trillion ecosystem, which is the modern AI ecosystem. Okay. So my name is Puru Kathuria. I am a software engineer by profession, and I worked at Google for 3 years. I started my career studying computer science at IIT Delhi. My specialization was in learning, machine learning, and AI. At that time, AI was very uncool. But it was not that cool, it was not that hyped. So we used to study it with the lens of academia, a lot of theory, a lot of book reading, a lot of proving the lemmas and theorems. And then we got into applied AI because we wanted to get into the industry as an applied scientist, as a research scientist, as a machine learning engineer. So I started my internship at MathWorks in 2020, and I started working as a software engineer intern. And I used to work on motion planning algorithms for self-driving cars. Then I grew into a software engineer role. So motion planning of self-driving cars allowed us to experiment a lot with complex algorithms and deep learning, because we wanted to recognize what's there on the road. If a car is moving on the road, in the road scene, we wanted to recognize what all objects does it have. So that was the most common problem that we wanted to solve in the scene generation and scenario generation for a self-driving car. Then we wanted to plan the motion also, right? So we dealt with a lot of geometry and deep learning problems at MathWorks. Then I switched and went on to pursue software engineering at Google. And at Google, I worked on cloud security. So in the whole software engineering domain, I have gotten gist of two angles. At MathWorks, I got to solve a lot of complex mathematical problems, which did not have that much of scale. But at Google, I got to work on large scale distributed systems. So at MathWorks, we were not dealing with million QPS. At Google, we were dealing with more than a million QPS and a lot of scale, right? So there we got introduced to the idea of distributed systems. And at MathWorks, we got introduced to the complex idea of deep learning and geometry problems. So I've been very grateful to get the gist of engineering with both the dimensions. And then we started Lex AI. So I'll tell you a small anecdote. I think this has been always my habit to get onto the stage and talk about machine learning and deep learning ever since. So at MathWorks, I started a deep learning book club with a guy named Atul. I don't know if he remembers me now. So that deep learning book club took a book by Ian Goodfellow. Sir might have heard of him. And he's a legendary deep learning author. And we thought to complete that book as a community. So we made a community at MathWorks that, read one chapter each and we'll discuss that chapter every weekend. So on Fridays, we used to sit. We never completed the book. So that entry just got into my resume. We went on for 6 to 8 weeks to run the deep learning book club, but we did not complete it. At Google, again, I started teaching machine learning to software engineers and engineering managers. So I used to gather all the people in a small room on every Friday at Google, especially the Gurgaon office. We used to come together, all junior engineers to senior engineers, program managers, engineering managers. We used to sit down and I used to teach them machine learning. They used to enjoy it. It went on for 8 to 10 weeks. And that's how I realized that, we have to do something, the intersection of AI and education. We have to have a lot of products that make learning easier. So that's when we thought, let's start something around Lex AI and, make education and AI a little fun and a little cool. I also started this deep learning talks, an internet episode series on YouTube. So we talk about a lot of complex ideas and topics about deep learning on YouTube. So you can see a pattern here. Wherever we get a stage and a chance, we talk about machine learning, deep learning, and AI. Right. Yeah. So the thesis of this talk is to highlight the unknown men who have given rise to the $1 trillion industry and made trillions of dollars of wealth for a lot of people. So the first breakthrough, who all have heard of the paper attention is all you need? Anyone? Okay. Who all uses GPT? Okay. So chatgpt.com is a conversational AI. Behind that sits a large language model. The large language model is nothing but a decoder only transformer. That decoder is inspired from this paper known as Attention is All You Need. So this one paper changed the world. So people call it, in the industry, it is famous as the $100 billion paper. So it came out by Google. It came out of Google by a guy named Ashish Vaswani and a lot of other people. So it's a very, very famous paper. This was one of the fundamental breakthroughs in deep learning. Now, this is very boring breakthrough because, we don't want to study the architecture right now, right? So the second breakthrough that I want to talk about, which is super interesting, which has genuinely given rise to the big bang of AI. So, to the modern AI ecosystem that has created trillions of dollars of wealth. So there were these two kids sitting in Toronto, in University of Toronto in Canada. One was named as Alex and one was named as Elias. Both of them were working on a computer vision problem. They wanted to solve image recognition and they were working with this guy named as Geoffrey Hinton. Anyone who has heard of Geoffrey Hinton? So Geoffrey Hinton is the godfather of AI. He invented deep neural networks and backpropagation. So he has also received the Turing Award. So he is known as the OG godfather of AI. And if people are working under him and they are trying to solve a problem, I think all of us should take it seriously. I mean, especially the folks from the AI industry. So they invented something known as AlexNet. It was named behind the guy Alex. So the other guy, Elias, was also part of inventing AlexNet. Elias also went on with Sam Altman to co-found OpenAI. So Elias and Sam Altman were two of the co-founders of OpenAI. Then Elias left OpenAI and went on to start Safe Superintelligence, right? So Geoffrey, Alex and Elias, these three people, these are the three guys. So Alex is this one, the nerdy one, and he is Elias, and this is Geoffrey Hinton, their professor at University of Toronto. No fancy university in the US, no Ivy League here, right? Then there is another guy named as Jensen. Anyone who has heard of Jensen? Jensen is the CEO of NVIDIA. Anyone who has heard of NVIDIA? Jensen Huang is the CEO of NVIDIA. NVIDIA, you might have used, if not to train your deep neural networks, you might have used for gaming. You might have access to their graphic cards, right? So Jensen is struggling with his company and he has made a couple of billions of dollars, but he's still wanting to stretch the valuation of his company and is looking for a breakthrough. And these two kids in Toronto, they are working on an image recognition problem, no correlation. Right. Jensen is sitting in Silicon Valley and they are sitting in a boring town, a boring city, Toronto. So these two kids invented something known as a convolutional neural network, which is a deep neural network that solved image recognition. So their neural network performed the best in all of the 30 years in image recognition on the classical dataset known as ImageNet. So ImageNet is a very complex dataset. It has millions of data points and couple thousand classes. So they invented a deep neural network that crossed all the benchmarks. Now Jensen was noticing this because Geoffrey Hinton is working on deep learning. Andrew Yang at Stanford is working on deep learning. Yann LeCun at New York University is working on deep learning. So he's trying to notice all of these guys. So the CEO of NVIDIA he has no correlation right now, deep learning as of now. Jensen used to solve computer graphics problem. That is also one of the hardest problem to solve, right? With his GPUs, with his graphic cards that we know of, right? So he's not noticing all of these people. When he saw AlexNet come out, he was not interested in the architecture of AlexNet. He was interested in how did they train and run AlexNet. So this guy, Elias, he's a very frugal guy. He wanted to save some money. So he picked up two GPUs from NVIDIA. NVIDIA used to run on CUDA. Anyone heard of CUDA? So CUDA is a programming language used to program NVIDIA's GPUs. He wrote some parallel programs for the computation of his neural network on CUDA. As a hack, he used two GPUs to run his neural network, and Jensen noticed it. When Jensen noticed this thing, that this simple computer graphics problem, the hardware for this computer graphics problem, the silicon behind it, can solve deep learning problems. This was the big bang moment of AI, because then he went on to tell everyone who's working on deep learning that I have something that you might need. I have the hardware for your machines. The second big bang moment from this particular insight was a deep neural network was thought of as a universal function approximator. What I mean by that is, you take any deep neural network, give it sufficient amount of data, it is going to represent that data in higher dimensions and learn that representation, which is also known as representation learning, and it's going to produce an output. So Jensen also noticed the first thing is that our GPUs, our graphic cards can solve parallel computation and help train a neural network. Second thing is, neural network can solve universally all the problems in the world across all the modalities. So no matter what modality you are dealing with, if you give large enough data, the only condition for a neural network or a universal function approximator is that it should have an input and it should have an output. You give it any input and it's going to learn and it's going to produce an output. These are the two things that Jensen noticed, and at that time NVIDIA was valued at $4 to $5 billion in 2012. Today, NVIDIA is valued at $4.5 trillion. That's when they started this boom, the big bang moment, that we are going to be the monopoly behind the training hardware of all neural networks, and deep learning can solve any problem. These guys, especially this one, made billions of dollars through OpenAI. And Alex went grounded. He did not care much, and he still moved on to work on convolutional neural networks, right? So this is one NVIDIA GTX 580. Only two of these were used to train AlexNet, which came out as the best image generator of all time. Jeffrey Hinton, when all of these things were happening, Jeffrey Hinton had this theory, and all of these people had this theory that all the radiologists will go out of jobs because of our image recognition solution, right? So that's why this particular moment mattered a lot, right? So we have seen three dimensions now. The first is that AlexNet had great architecture and it solved image recognition. The second is deep neural networks can solve almost any problem given and across different modalities. The third is that neural networks can be seen as universal function approximators. They can approximate any continuous function which has an input and can produce an output. So these were the two observations that Jensen saw. And now we can see the scaling hypotheses, the scaling laws that come into picture. Bigger models lead to better results and lead to the best performance. Now, as you guys have already heard of machine learning and deep learning, you already done the course, just have a look at how we have evolved. So the first linear model that people might have seen, a simple line model, y is equal to mx plus c. I am sure all of you might have seen this model, which is nothing but a simple linear equation, y is equal to mx plus c. Then we thought, yeah, we need non-linearity. We cannot only go with a linear model. How do we inject synthetically some non-linearity? We introduced the idea of sigmoid, the activation function, and we wanted to solve classical classification problem instead of a regression problem. So from linear regression, we evolved to logistic regression by applying a sigmoid function. Then the idea of the neuron, treating the equation as a neuron, right? And so that we can give rise to something known as a neural network. The same equation that we used here is also modeled or perceived as a neuron. So because it's nothing but y is equal to mx plus c, which is w transpose x plus b, and you apply a nonlinear activation. So now you have non-linearity also, and you are doing the weighted average of your input along with the weights. Then came neural networks. When we stacked these neurons in an input layer, a lot of hidden layers and an output layer, then we gave rise to neural networks. Then the equations became a lot nested across layers. We stacked a lot of neurons vertically and horizontally in order to build this neural network. The next invention was the convolutional neural network because we wanted to solve image recognition. Neural networks were general purpose. Convolutional neural network with a convolution block solved image recognition once and for all. And it's super relevant because AlexNet was a CNN, right? And 2012, if NVIDIA had not noticed the Big Bang moment, there would not be $4.5 trillion of wealth with NVIDIA, and the AI movement would not have been at this particular stage. And we would not have, if Elias and Alex and Geoffrey did not notice that this hack can be used to production. I can use a graphic card that helps people render images on their gaming. I can use those graphic cards in order to produce or parallelize my computation for neural networks, because neural network is nothing but matrix multiplication, right? So if they had not noticed that simple hack to save money, we would not have NVIDIA as an AI chip company. NVIDIA used to be a graphic card company, now it's an AI chips company. Now they no more say that we only sell gaming chips. They always say that we sell AI chips, right? That's how NVIDIA found its breakthrough. So one more interesting fact about this whole narrative, that we have a lot of technology companies. We have Google, we have NVIDIA, we have OpenAI. We have so many technology companies that we also call the big tech, Amazon, Microsoft. All of these technology companies are selling either advertisements or consumer electronics, right? Like Apple and Google and Microsoft, right? NVIDIA is the only company that literally sells technology. NVIDIA don't sell ads. They don't sell any consumable electronics. NVIDIA is the only company, and it's the biggest tech company that only sells technology as a pure business, nothing else. So this is also one of the facts in Silicon Valley. So I mean, Jensen realized one more fact, that Jensen has been the longest running CEO, tech CEO ever, for more than 33, 34 years. So if Jensen would not have realized the Big Bang moment, we would not have the modern AI systems. So after convolutional neural networks, we wanted to solve sequences. Why sequences? Because language is sequence. We wanted to model language. We had a lot of NLP based algorithms in the classical machine learning era, but pretty slow, right? And they were not able to produce the way that we needed, and they were not leveraging neural networks to the max. We invented something known as a recurrent neural network, one of the most complex neural networks, right? So because it has recurrences, it has a recurrent loop. So The memory in recurrent neural network is defined by its hidden state. It's the most famous equation in case of a recurrent neural network. This equation solved sequence modeling once and for all. We were able to predict the next talk given the input sequence of past 10 days. We were able to predict the next word given the past t-1 tokens, right? So we were able to do all the next token prediction even with sequence modeling. The problem with the RNNs and LSTMs, which was also a sequential network, the problem with them was that it was stupid. Why it was stupid? Because it was very tightly coupled to the last word. It had tight dependency on the last word. So all the parallel computations we had to do was sequential. We had been innovating a lot in hardware, we invented GPUs. But in algorithms, we are not able to invent parallel algorithms. We are still doing sequential computations. That's when this paper, the breakthrough that we talked about, which is attention is all you need. This paper fundamentally changed the dimension of sequence modeling. That's why we have LLMs today. How it changed? Because it introduced one simple equation. I mean, it's not that simple, but one equation, which is the idea of attention, self-attention. We also call it the scaled dot product. Right? So it's a scaled dot product of query and key divided by the square root of dk. So this equation said that you don't need to maintain context sequentially. You can maintain global context in a global fashion. You will just have an order of n square matrix and you will be able to have store the relationship between any token I to any token j in a parallel fashion so that you can do all the computations parallelly. So this was a natural extension from RNNs to transformers. Transformers were introduced with the idea of self-attention, cross-attention, multi-headed attention. So all in all, just one formula of attention. Now, got introduced to three transformers. One is the encoder-decoder transformer, which used to do translation, English to French, English to Spanish, any language A to any language B. OpenAI did a clever thing. They took out a small subsection from the architecture, the encoder-decoder. They said, let go of encoder, we don't need it. Just give us the decoder so that we can predict the next word. Put decoder only transformer and made the first large language model. Democratized the first large language models. I'm sure people must have discovered the first large language model way before OpenAI, but OpenAI marketed it really well that it reached us. So the whole GPT family, GPT-1, GPT-2, GPT-5 till 5, everything is a decoder only transformer inspired from this one single paper, which is attention is all you need. That's why it's one of the most fundamental breakthrough. That's why it's called as a $100 billion paper. Now there's one more small anecdote that I want to share since we have some time and I'm sure we're not getting too math heavy. Now there's another guy named as Moore. Anyone who has heard of Intel as a company? Yeah, so he's the co-founder of Intel. In 1985, if I remember correctly, this thing was coined, Moore's law. So he had a hypothesis that every 2 years, the cost of computing is going to reduce by half and the performance of your computers is going to double. That's why we see that technology keeps on getting more complex. We keep on adding more and more transistors. We keep on adding more and more cores and even the technology is getting cheaper. So Moore's law had this hypothesis which has been playing out for so many years now. I don't want to say 128 years, but yeah, people say that it has been playing out since 128 years now. Moore's law is still in practice. NVIDIA again took inspiration from Moore's law and said that we want to invent something known as NVIDIA law, which is nothing but Moore's law on steroids. Moore's law only states that we are going to double the performance every year. NVIDIA's law or Jensen's law states that we are going to 10x the performance of compute every year or every 2 years. And we are going to still keep on reducing the cost by half. The first GTX, I think the name was Spark, that he gave to Elon, the GTX Spark that he gave to Elon Musk, I hope I'm pronouncing the name correctly, costed $4,000. And the first graphic card that he made costed them $300,000. Right. So look at the cost, $3 lakh to $4,000. How Moore's law also came into practice at this time. Yeah. And if we talk about the GPT family, the first GPT that came had couple 100 million parameters, 117 million to be precise. And right now, all the flagship models of the GPT family, so GPT-4 has at least 1 trillion parameters and GPT-5 even more than that, right? So this costed us billions of dollars to train, this still costs us billions of dollars to train, right? So we can ideally see that the cost is also getting reduced, right? So for hundreds of years, we have seen that Moore's law has been in practice and this is also a significant pillar in the whole modern AI development, the new market, the new ecosystem that we have been brought into. Why I keep on calling the new ecosystem? Because everything is trying to change from now. So just like I was interacting with the folks, we used to code a lot during our engineering, but today we have stopped coding. The only thing that we do is provide intent to our agents. So all of us as software engineers in the industry use state-of-the-art tools like Cursor, like Claude Code, and some flagship tools internally that we used to use at Google. All we do is communicate our intent to the agent, and the agent helps us facilitate all of that code. So everything, right from learning to building, is changing. And the pace at which we are able to ship software now has grown by I don't know how many thousands of X. So before we move on to the questions, there's one more thing that I wanted to talk about. So why are these people so obsessed with AI? The Jensen, Demis Hassabis from DeepMind, Dario from Anthropic, who has invented Claude. Why are these people so obsessed with AI? All of these people want to build something known as AGI, Artificial General Intelligence. They want to maybe invent, I don't know if it's even a word, synthetic biology. They want to, so right now we are mimicking human intelligence. Now we don't have real intelligence. We are mimicking human intelligence. They want to have a system that is capable of doing everything that humans can do. Now, it obviously, if it's capable of doing everything humans can do, it will be able to think also. It will be able to walk also. It will have its body also. So it should be an embodied AI, right? So that is what we are calling artificial general intelligence. An agent that has capability and can do all the tasks 100% better than human beings. All 100% of the tasks better than human beings. That is what is known as AGI, artificial general intelligence. That is what they are trying to solve, because their hypothesis is that if we come to an AGI state, it's a superficial state, it's a assumed state, it's not a real state. If we come to that state, then we will be able to solve all the fundamental problems for humanity, even cancer. So that is the whole hypothesis. But the main blockers right now in solving AGI, the first blocker is continual learning. Anyone who has trained neural networks before will definitely know once you stop the training process, once your backpropagation is done, you freeze the weights and you deploy it to inference and to query it. Right. So continual learning is a phenomenon, is an idea. What if neural networks could learn and update their weights every second? When they are deployed in the real world, what if they could learn every second and keep on updating their internal representation in higher dimensions? So continual learning is one of the breakthrough that we might expect from these top companies before we go to AGI. The second breakthrough is reasoning, causal reasoning. Right now, everything is not being answered by the large language models. They don't know what caused this. Causal reasoning, just like human beings do, the neural networks cannot do that better. They have chain of thoughts, but that is linear. They are trying to invent tree-like chain of thoughts to reason in a mathematical way, but we have still not solved causal reasoning, just like human beings. If we are able to solve causal reasonings, we will also have to teach the models the most fundamental thing that explains the universe, which is physics. If our neural networks can understand the idea of physics, thermodynamics and liquids, how objects behave in the real world, then we will have something like a world model which understands the world better. Large language models have only read the information about the world because they have been trained on the internet data. Vision language models have only seen the world, but world models will have also experienced the world as an agent through simulated environments, right? So that's a totally new fundamental paradigm that they're exploring, which is world models. So these are the three problems that are still being explored at all of these top tech companies: continual learning, world modeling, and causal reasoning. So we have not solved all the problems in AI as of now. We're still planning, we are still expecting a couple of breakthroughs before we reach AGI, right? So now the last two closing questions that maybe we can take. The first one is, I think, a big dying question, right? Will AI take our jobs? Do you guys also wonder this? Do you guys also wonder about all of these things? The first question. Anyone who has thought about this question? Yeah, so I'll give you an anecdote. I'll give you one of the anecdotes that might help you build a mental model to think about this. So Geoffrey Hinton had this hypothesis, who invented backpropagation and deep neural networks in University of Toronto. He's also a recipient of the Turing Award. So when he says we should listen, highly opinionated people, highly academic, right? And made a lot of money, wealthy of information, wealthy of wealth, have a lot of wisdom. So I think it makes sense to listen to these guys. He had a hypothesis that all of the radiologists will go out of job because we have solved image recognition. They said that all of the radiologists in the US and in Canada will go out of jobs. I think there were approximately 2 lakh of them. This is back in 2012 because they had solved image recognition. Now we might be assuming that, okay, there might not be any job as a radiologist. But what we found a few years later, there were more requirements for radiologists. Now, why this happened is the question. Why such a contrarian thing that happened, right? So we needed more radiologists because all the existing radiologists were able to process more patients faster. The purpose of a radiologist is not only to see images, it is to diagnose the patient. So they could see more images with more precision because of the image recognition systems, and they were able to diagnose more patients. The hospital also thought that my productivity as a hospital has increased because more economic activity is happening. Because I'm able to diagnose more patients with my existing radiologist, I think I should hire more radiologists. There is immense amount of demand for the diagnosis that the radiologist has to do, right? So a lot of radiologists also went out of jobs. So the key idea is, what is the purpose of your job? If your job is only a simple task, or if your job is equal to the task, you will go out of business. There is no doubt about it. But if there is a bigger purpose to your job than a task, then you will survive and maybe thrive. So this is one of the mental model that you can use. There's one more mental model around chauffeurs. So a lot of people use drivers these days, chauffeurs, right? Even in the US and India. In US, it's far expensive than what it costs in India. Once Elon Musk has democratized all the self-driving cars, will my driver go out of job? Any guesses? Will all the drivers and chauffeurs go out of job once we have self-driving cars? This is common sense. I think that's a good guess, mostly. So, but there are some chauffeurs and drivers whose purpose is not only to drive the car, also to protect the car owner. Sometimes to protect the car, if you have a prestigious car. Sometimes for their hospitality and to make the car owner feel good. They will not go out of job. There are some drivers and chauffeurs who drive cabs. They might deploy more cabs because we are trying to commoditize the technology. So they might change their jobs. A lot of chauffeurs will change their jobs. A lot of chauffeurs will go out of job. But the people who will stick in the jobs, their purpose is bigger than a simple task, is the mental model that you guys can take. Now the second question is, as an engineer, what should I optimize for? What the hell should I learn? If coding is not required, if Cursor and Claude can do coding better than any Google engineer or any other competitive programmer, why the hell should I learn to code? What should I learn in order to make a lot of money or in order to get a job, whatever is the ambition? As an engineer, what we should optimize for? I don't have super solid opinion, but I have a lot of opinionated people who I follow and I read about. So this guy, Andrej Karpathy, anyone who's heard of him? Okay. So he's also one of the key people. AI is one of the biggest engineer that people admire. He's also very famous on YouTube. So he is one of the co-founders of Tesla Autopilot. I mean, he was heading the team of Tesla Autopilot. He's also had his research experience at OpenAI. So he belongs to a great pedigree of companies. Right? Now he's building stuff of his own. And then there is this guy, Demis Hassabis. Let's ask them, what should an engineer optimize for? The bare minimum an engineer can do is adopt all the AI tools as fast as possible. That is the bare minimum. All the innovation that is happening, at least you have a first mover advantage in adopting that innovation. Now, second best thing is what an engineer can do is have very solid fundamentals of all of these AI systems. Now, why do they say that? Let's go back in time. In 1958, when Fortran was invented, we all have heard of Fortran programming language. That was the first high-level programming language, right? Before that, we used to write a lot of machine code and hex code. All the people. So we all understand the concepts of Pandits and Brahmins, right? Who are kind of the priests for our god, right? Originally we had very small cohort of them. Similarly, there were programmers who were very small in numbers who knew how to write that machine code. They kept on doubting that, man, Fortran cannot write better code than me. Compilers were invented the next year, I think 1959. Compilers came into picture and then they again argued, I can compile better code than this compiler. Whenever any new technology comes, we humans are very pessimistic in adopting that technology. We get very scared. Who all thrived in that era when these new technologies was coming? People who thrived in this era, they adopted compilers. They understood the fundamentals of compilers, how compilers are functioning, and they started building one layer on top. You might see, just like Moore's law, we have one more law, which is the abstraction law. Every year we're trying to abstract the problem and growing up the pyramid. Pehle we used to write machine code, now we are writing code in understandable self-explanatory keyword-based languages. Then we are writing in super high-level languages like Python. Now we are simply writing in English language. So we keep on growing up the ladder. We're abstracting out all the details in the pyramid, right? So the engineers who are going to thrive, obviously, are going to be the ones who have super good fundamentals for all the modern AI systems that are being built. And the bare minimum is that they have adopted. So the bare minimum is you adopt all of these AI tools, because there is no development outside of them. So if I am doing AI powered development and you as a business are competing with me in doing manual development using a big team of, let's say, 10-20 people, I can outrun you any day. So the whole AI powered development is a lot intent based, is a lot agentic in nature, because we have multi-agent systems that can facilitate code faster than human beings and write code more efficient than human beings. And these systems will keep on growing better and better, faster than how a human can learn. So the bare minimum is that we adopt these tools. The second best thing, or I think this should be the first best thing, that we should have super strong fundamentals, deep mathematical principles, deep computer science principles, in order to understand these sophisticated systems, so that we can leverage them and build something meaningful. So I think these are the two opinions on these two questions. So I've made so many videos, I've given so many talks, but I never know how to end a talk, right? So I always mess it up. So I think right now I've stolen a quote from somewhere. It's deep rooted in me. It is also very much valid for an engineer. So I'm a true engineer or a true artist if I'm able to start from first principles, learn the best known art and reinvent it in a way that it has never been before, right? So I think we should all have this kind of philosophy, especially in this modern AI world. And the second thing, which is a bit controversial, AI might not take your job, or it might take your job, but the main macroeconomic trend that all of us can observe is the jobs are definitely getting reduced. If X company hired 1,000 employees in 2022, they are hiring far lesser employees, and at 70% of the salary that people used to get and negotiate in 2022, 4 years back, has fundamentally reduced. So one thing that we should learn is, which is a little difficult, how to also be employable and make money independently, because that is going to be a very key skill. We will see that a lot of entrepreneurs will emerge straight out of college. Building software is easier than ever. Writing presentations, pitch deck, building any digital asset, software, media, content, presentation, thumbnail, whatever, you name anything, is far easier than ever. We will see a lot of budding entrepreneurs that will come out. We will see a lot of micro economies being established, because there would not be a lot of jobs, and we human beings are survival beings. We will figure out and do anything just to survive, right? So if there is no job, I will figure out my own job, right? So that is a very good mental model that people can adopt. And people who don't want to take the entrepreneurial path should definitely work a lot on the modern AI tools and understanding all the fundamentals of these AI systems, so that they can leverage them in both the dimensions. I think, yeah, that's it from my side. Thank you so much for paying attention.